In this part, the flyback regulator is explained. It is the first isolated type DC to DC regulator in the classification of switch mode power supply. It is basically derived from the SEPIC regulator. Let us first of all have a glance at the construction of the flyback regulator. It has one controlled switch which is MOSFET, and it is a high switching frequency component, transformer for the isolation purpose, diode for the freewheeling action, capacitor for the filter purpose, load, and if the DC supply for this regulator is readily not available, then uncontrolled rectifier which can produce DC from the available AC. Same as other circuit diagram, the flyback converter has one controlled switch, so the one cycle operation of the flyback regulator can be explained with the help of two intervals. The first interval when the switch is on, and the second interval when the MOSFET is off. So here you can see the equivalent circuit diagram for mode 1 operation and mode 2 operation. The highlighted portion in the equivalent circuit diagram shows the active part during that mode of operation. Let us understand the working of the flyback regulator. So when the MOSFET is turned on, mode 1 operation begins. So when the switch is made on, at that time the primary winding gets connected to the supply, and the voltage appear across the primary winding is equal to supply voltage. The corresponding voltage V2 in the transformer secondary. So by using the voltage and transformer turns ratio, we can easily find out the voltage appear across the secondary winding, which is nothing but V2 divided by V1 is equal to N2 divided by N1. So by substituting V1 is equal to Vs into this equation, and when we make V2 as a subject of equation, we get V2 is equal to Vs into N2 divided by N1. So voltage across primary winding is equal to Vs, and voltage across secondary winding is equal to Vs into N2 divided by N1 when the MOSFET is in the on state condition. During the first interval, the polarity on the secondary winding is like the dot end terminal is the positive and the other terminal is the negative. That negative polarity appears at the anode of the diode, and because of that diode is in the reverse bias condition and it does not take part into the mode 1 operation. So V2 reverse bias is the diode D, and filter capacitor C, that is this one, is large enough so that the capacitor voltage or the load or the output voltage is taken as the constant. So during the first interval, this capacitor takes care of the load. For the magnetizing current, the current which is flowing through the transformer core, it is assumed that the transformer core is not demagnetized completely at the end of the periodic time, which means that we are considering the continuous conduction mode. The transformer core has always some amount of energy. So here you can see that the behavior of the parameters with respect to time. V1, that is the voltage across the primary winding. So during the on time, the voltage across the primary winding is equal to supply voltage, and during the same time, voltage across the secondary winding is nothing but N2 divided by N1 into Vs, right? So here the transformer core serves as an inductor for the converter. So the magnetizing current during the on time gradually increases from the minimum value towards the maximum value. The minimum value is Im0 and the maximum value is Im1. And during the first interval, because diode is in the reverse bias condition, so the ID is equal to 0. So in other words, the transformer magnetizing current at t is equal to 0. That means at this instant the magnetizing current is not 0, right? Because we are considering the continuous conduction mode. It has some positive value which is nothing but Im0. So during this on time, the current rises from its initial value Im0 to Im1 at the instant t is equal to t on. During this rise, the magnetic energy gets stored into the transformer core. So this rise in the magnetizing current can be expressed mathematically as Im of t is equal to the magnitude of magnetizing current at instant t is equal to 0 plus rise in the magnetizing current with respect to time, which is in the interval 0 to t on. So that gives us the expression Im of t is equal to Im0 plus Vs divided by L into t. And at t is equal to t on, that means at this instant we can write Im of t on is equal to Im1. Why? Because at t is equal to t on instant the magnetizing current reaches at Im1 value. So Im1 is equal to, here we are substituting t is equal to t on. So Im0 plus Vs upon L into t on. Mode 2 operation. So when the power MOSFET is turned off, the mode 2 begins. We know that the polarity across the winding get reversed when the switching action takes place. Right, so here you can see that the dot terminal has become negative and the other terminal has become the positive, and these polarities get reflected on the secondary winding, and because of that the upper terminal has become positive, and due to that the diode, anode of the diode becomes positive and diode comes into the forward bias condition and it becomes on. So the EMF induced in the primary and the secondary windings are reversed. Diode D is now the forward bias, and a current in the transformer secondary winding begins to flow through the diode D, which means that whatever energy is stored into the transformer during the previous interval, that energy gets released into the load via this freewheeling diode D, which means that current starts from this terminal of the secondary winding, it passes through the diode, it passes through the load, and this is how the closed loop path is formed, and the energy gets delivered into the load from this transformer. So the magnetizing current reduces from the maximum value Im1 to Im0 by the time instant t is equal to t, and the transformer core energy gets released into the load. So during the t off, voltage across the secondary winding is equal to minus VO. When we apply the KVL in this loop and when we make the V2 as subject of equation, we get the voltage drop across the secondary winding is equal to minus output voltage. From that we can easily find V1 using the voltage and the turns ratio relationship. So V1 is equal to minus VO into N1 divided by N2. So the fall of magnetizing current Im during off time can be expressed. So mathematically we can express this decrement in the magnetizing current Im as Im of t is equal to Im1 minus V1 divided by L inside the bracket t minus t on. So when we substitute t is equal to capital T into this equation, we get magnetizing current at the instant t is equal to Im1 minus N1 divided by N2 into VO into 1 upon L, and here the t is substituted, so we get t minus t on. Right, so here in the waveform you can analyze the behavior of the parameter. So during the second interval the voltage across the secondary winding is equal to minus VO, And during the second interval, voltage across the primary winding is equal to minus N1 divided by N2 into VO. And as the energy is released by the transformer core into the load via the freewheeling diode, the magnetizing current reduces from the maximum value Im1 towards the Im0. So by substituting value of Im1 into the previous equation, we get Im of t is equal to Im0 plus Vs upon L into t on. That's what we have substituted into the previous equation, and minus N1 divided by N2 into VO into 1 upon L t minus t on as it is. Since the net energy stored in the core over the periodic time t is equal to 0, which means that steady state condition, the energy stored by the transformer core and the energy released by the transformer core both are same. That means the magnitude of the magnetizing current at the instant t is equal to 0 and at the end of the cycle is same. Hence we get Im0 is equal to Im0 plus Vs upon L into T on and minus N1 divided by N2 into VO into 1 upon L into T minus T on. Right? So on the left hand side and the right hand side, both side Im0 is present. So when we send this Im0 on the left hand side, so Im0 minus Im0 is equal to 0, and by sending this L uh, of this denominator on the left hand side, also that goes out. And finally, when we do the simplification, we get Vs into T on is equal to VO divided by A inside the bracket T minus T on, where A is nothing but the N2 divided by N1, number of turns on the secondary winding divided by number of turns on the primary winding. So the load voltage can be given as V output in terms of the supply voltage as A into T on divided by T minus T on. Right? So when we divide the numerator and denominator by T, then we get A as it is, Vs as it is, and T on divided by T, that can be written as the duty cycle for the flyback converter. Here when we divide the denominator by T, that means T divided by T is equal to 1, and here T on divided by T is equal to K. That is again the duty cycle of the flyback converter. So output voltage depends on turns ratio as well as the magnitude of the duty ratio in the flyback converter. And the flyback converter mostly used in the applications below the 500 watts.